This is a lesson on integrals in the Basics of Calculus for Physics unit of my curriculum. I put together a lesson with a brief instruction on how to do integrals. I don't go into that in depth. And I also chose a small array of problems, example problems for us to work through that will be useful from what I've seen in physics, anticipating what you're going to be approaching and working through in the material. The largest idea for an integral is that the integral is the antiderivative. So by this point in calculus, you should know how to take derivatives. And so what the integral does is say, well, if I know the derivative, if I work backwards, I should be able to figure out the original function. So we know that f prime of x here is the derivative of an original function, f of x. So when we use the integral notation, we're going to take the integral of the derivative with respect to x. This dx tells you what variable with respect you're taking the integral, and then you'll get back the original function, and then some arbitrary constant, which I'm going to talk about in a second. The integral also gives the estimate of the area between the curve, and this is the derivative, and the x-axis for the given function, the derivative. Okay, so I'm going to talk about that in a little while. I do have a first example here. This first example here is I just have a line, and I'm telling you the derivative of a function is a linear function. The derivative is linear. So when I look at this graph, I see that I know the derivative is the tangent line, the slope of the tangent line to the original function f of x. Okay, so when I look at this, I think, okay, the slope of the tangent line to the original function is a negative value, and then it goes to 0 here, and then it becomes a positive value. And if you've done derivatives before, you know that the original function was a parabola. So what I'm going to guess on this function here, just looking at the graph, I can kind of think about what the original function was. It has the tangent line to the original function, has a negative slope, goes to 0, has a positive slope. I'm kind of inferring, appealing to your knowledge of derivatives. In order to get a 2x, in order to have x to the first, when I took the derivative, I began with an x squared. So I know that the original function, f of x, is a parabola. Okay, so when I'm looking at that on this graph, I'm going to say, oh, well, the vertex happened at this value, x equals negative, what is that, 1.5. Okay, that's where the vertex was. That's where the turning point is. And if you think about a parabola, I'm just drawing this generally in here. This isn't accurate for this function. But you can see that the tangent line is a negative value up until that point, and then it becomes a positive value. Okay. So when I'm thinking about the derivative and the original function, I see this relationship between them. And we're already looking at, well, if I know the derivative, what was the original function? And you can kind of see this general rule coming out for the power rule. The power rule, and we're looking at an indefinite integral. There's no endpoints on our integral. I'll get to that in a few minutes here. But if I know the original function, or if I know the derivative, f prime of x, all right, and I'm saying that that is some power of x, then when I take the integral, what I'm going to do is take that n and I'm going to add 1 to it. All right, so that x gets a new exponent. And out front, what I need to do is divide by n plus 1. Okay. So again, when I think about the derivative, if I let the original function f of x equal x squared, the derivative of that is going to be 2x, right? I subtract 1 from the numerator, I'm sorry, I subtract 1 from the exponent, and I bring down the exponent to the front, so that's how I get the 2 out front. Well, I'm just going to undo it. So if I subtract 1 here, then I'm going to have to add 1 in order, if I know the derivative is 2x, I know I'm going to have to add 1 in order to get the original function. And then also this term out front, remember we brought down the 2 to begin with. Well, in order to get the original function, that means I need to divide by the half. And I still have the 2 out front here. All right, I need to divide by that in order to get the original function, right? If my original function was x squared, when I multiply 2 times a half, then I get my original function back, x squared. Okay. Often what I see students have trouble with is they still get used to taking a derivative rather than taking the integrals, so they'll subtract 1 rather than adding 1 up here, and they'll forget to divide by the new exponent. That's what you're doing, is you're dividing by that new exponent. Whatever that new exponent is, you divide by it. Okay, so it's a little bit of practice. Notice also here that I have the multiplication rule here. When I take it, if I have some constant, I don't know, let's call it a times x to the n power, I can just bring that outside. Just like I did with derivatives, right? If I have 3x squared, I take the derivative, I take 3 times 2x, and the 3 just sits there and I end up multiplying it in. Well, that's the same thing with an integral. Let's do this for the line that I had, right? This is the function that I started out with. So I have the heuristic rule up here. To be able to take the integral. I know that I'm going to end up taking the integral. Oops, sorry about that. 2x plus 3 dx. In order to find the original function, I'm going to plug in the derivative here, and then I'm going to integrate it. Okay. And again, we can use the multiplication rule. We also have some addition, and so what I'm going to note here is, and you'll see this with integrals, we're going to do a little bit of algebraic manipulation here. I'm going to distribute the dx to both of these terms. I'm going to get the integral of 2x dx plus the integral of 3 dx. Okay, I'm going to do a multiplication rule. I'm going to bring the 2 outside of this integral, the integral of x dx. All right, 2 is just a constant. I can bring it outside and multiply it. I'm also going to note that 3 is a constant. I can bring that out, the integral of dx. That may look weird, but there's, you may be able to think of it this way, is that maybe it leaves a 1 here, or an x to the 0th power dx. Okay, that might be a little bit easier way for you to think about what's the, if I, instead of just putting the integral of dx, I can put x to the 0th dx. And remember that I'm going to increase the, add 1 to that exponent of x. So let's work through this. I kind of already did this one on the previous slide, right? The integral of x dx, well, I'm going to have the 2 out front. There's a 1 here, so I'm going to get an x squared, and then I'm going to divide by the new exponent, 1/2. Okay, that's the result of this term here. I'm going to add on just the addition rule. I'm going to keep the 3. I'm going to add on plus 1 to my 0, so I'm going to get x to the first, and then I divide by my new exponent, which is trivial here because it's 1. Okay, so that is the result of this second term in the integral. I'm going to simplify this. I'm going to get x squared plus 3x. And if you're not sure, right, this is the original function. If you take the derivative of the original function, you should get the derivative back, right? When I take the derivative of this thing, bring the 2 out front, I get 2x plus 3. That's my original function. The one thing I'm missing on here, and you can, let's go back to this arbitrary constant. This is an arbitrary constant. Arbitrary. And I chose this example, plus c, right? What you're going to notice is, and I predicted this when we first saw this slide, this is a parabola. I can find the vertex, right? Negative b over 2a. Well, I'm going to have negative 3 over 2 times 1. And that's negative 1/2. I already said that. We expect the vertex to be somewhere along this vertical line. Where along this vertical line? Well, that's what this arbitrary constant says, right? I can have it +2, right? I could put the vertex here if I had a +2, or I could have a -2, right? If C is -2, C equals -2 here, C equals +2 here. The problem is we don't know what it is. Whatever this original function was, when we took the derivative of it, if there's a constant in this term, when we take the derivative, it becomes a 0 and we just lose that term. We don't know what it was, okay? So when we find the antiderivative, when we take the integral of this function, we're going to put a placeholder for this unknown constant. And if we were given some initial conditions, if we were given what that constant was, we'd be able to fill it in. But not knowing it, we're just going to leave this placeholder here. Another example for the power rule. This is a problem you might see in your homework. What I'm going to do to be a little bit more particular, I think this notation is a little sloppy. I'm going to put parentheses around here. We're going to integrate this whole function. I think when it puts the dx at the end without those parentheses, it looks like you're just integrated the -2 here, but we're integrating the whole function, and that can be indicated by where the integral sign starts. Okay, so we're going to find this term in here. The computer is already telling us that there's a plus constant on the end, which we already know. So what I'm going to do is, like I did before, I'm going to distribute this dx to each one of those terms. Okay, so I'm going to get the integral of 3x squared dx minus the integral of 16x dx minus the integral of 2 dx. All right, so whatever these signs are, that's why I put it in between here. I'm just doing the addition method rule here. I can also bring these constants out front. 3, the integral of x squared dx, minus 16, the integral of x dx, minus 2, the integral of dx. So I'm going to go ahead and take the integral of each one of these terms. I'm going to add +1 to the 2, so I'm going to get x cubed. I'm going to have to divide by that new exponent. I'm going to remember there's a 3 out front. Okay, so that's the result of that integral. I get minus 16. 1 plus 1 is 2, so I get x squared, and I have to divide by that new exponent. Minus 2, remember I have an x to the 0th here. I'm going to add on a +1, so I'm going to get x to the 1st. I divide by the new exponent. It's very trivial here. If it were me, I would just go say the integral of dx is x. Done. Okay. And then to simplify this, one last step here. 3 times 1/3 is 1, so I get an x cubed minus 8x squared minus 2x, and that's what I'm going to put in the box up here. Notice that I'm talking about indefinite integrals and definite integrals. A definite integral, when you look at this integral here, you're going to notice that there's an a and a b on the integral sign, and these are the endpoints. We call them endpoints or limits of the integration, and that's what a definite integral includes, is that it's not arbitrary over the whole length of the function, it's for a specific portion of the function. Okay, so when I take the integral of the derivative, I'm going to get the original function back, and then the notation we use is to put a line. It's just a line, and then the bottom one is always the beginning. You begin at A and you end at B. That's the notation, that's the convention. And in order to calculate this, what you do is you take the function evaluated at the end point minus the function evaluated at the beginning point. All right, and if you're, this is a physics sort of thing for me, that we always go final minus initial, right? That's how we do differences, is always final minus initial. So I have an example here. It's a little bit, again, repetition, and It's a little bit more complicated. I don't think you'll see functions this complicated with my curriculum. You may in a calculus curriculum. Again, I think it's a little sloppy here. I'm going to put parentheses around this dx. I'm going to notice my integrals. Notice that -3, your a will always be less than your b, right? Because this is the begin and this is the end, right? So we're going to evaluate from -3 to 2 this function dx. Okay, so I'm going to do this a little bit quickly. I'm not going to rewrite any of this in order to make it a little bit simpler. I'm just going to go term by term. I'm going to multiply 20 x to the 5th, and I need to divide by the new exponent. Minus 28 1/4 x to the 4th, right? Plus 15 1/3 x to the 3rd, plus 10 1/2 x squared, minus 12x. And then I'm going to evaluate that from -3 to 2. Okay, so you're going to see that, you know, I was doing step by step on the prior slides with the integral, but when you get good at it, when you get more proficient, you can do things a little bit more shorthand and a little bit more quickly. You may be able to see it a little bit. I would say the one thing that you may want to write out just to make sure you're showing all your reasoning and enough work when someone goes to grade your work is to put the 1/5 x to the 5th instead of just going, you know, 4x to the 5th right away. Okay, so that your logic and reasoning is a little bit clearer and more transparent when you're doing that. So that's that term. I already wrote it out. Minus 7x to the 4th plus 5x cubed plus 5x squared minus 12x, and we're going to evaluate all of that from -3 to 2. Okay, so what does that look like? Let me choose a different color here. We'll I like this color. What we're going to do is we're going to evaluate this function at 2. So wherever x is, I'm going to put in 2, and then I'm going to subtract off the same thing, but -3. All right, so 4 times 2 to the 5th minus 7 2 to the 4th plus 5 2 cubed plus 5 2 squared minus 12 times 2. All right, so that's that first term, right? This is f of b. We're going to subtract off f of a. So I'm going to put -3 in wherever I see x. 4 -3 to the 5th power minus 7 -3 to the 4th power. And watch out here, we're taking -3 to the 5th power and -3 to the 4th power. So watch out your sign here. You're going to want order of operations. You're going to put parentheses around this so it knows to take the 4th power of -3, not negative the 4th power of 3. That's a whole different thing. Watch out for your orders of operation. Plus 5 -3 cubed plus 5 -3 squared minus 12 times -3. Okay, so when you evaluate these, this term, this first term up here, is 52. All of this simplifies down to 52, and then I get a minus. The next term is it's -3 to the 5th power, right? We're going to get large numbers there. We're going to get -1593. So you could take a moment if you want and plug that through your calculator just to double check. I'm very confident on it, and when you evaluate this, we're going to get 1645. That is the answer for this indefinite, it is a definite integral, okay? So that's sort of the math way to do this. I haven't looked at any graphs on this. I've not really thought more in depth about what this represents overall, which I can do for you. Notice that our function f of x is, I guess this thing right here. That's our function here. It's x to the 5th power. We have an odd power, so it will be anti-symmetric around the y-axis. And it should cross the x-axis, what, 5 times? Maybe 3. There's not a plus constant out here, so I'm not sure exactly how to, but I did graph it. You're not surprised to know that I graphed this thing. Okay, so this is the original function f of x, right? It's goes x to the 5th power. We're going to see, notice that here's our endpoints. There's this 52. When I evaluate the original function at 2, I get 52 out. When I evaluate it at -3, I get the -1593. But what does that 1645? Remember, that was the answer. What does that represent? And what it represents is the purple area. This is a graph of the derivative. Right? That's a graph of this thing here. That's what this is, a graph of this. And what we're doing is we're finding the area between the derivative and the x-axis. So I highlighted it with purple area here. Notice that there's a large positive area here. There's a little bit of a negative in between here. With the scaling, I couldn't get it to show, really well. And then there's a little bit more down here. That's what the 1645 represents, is a bunch of positive, a little bit of a negative, and then a little bit more positive. When you add all of that area up, it's 1645. Okay, so that's what's going on in a graph. It's not this area on the original function. I think that might be a little bit of confusion, is what does the area represent? It's the area between the derivative and the x-axis, not the original function and the x-axis. I did like doing a graph of the original function because it gave me these two values, 52 and -1593, so that I could evaluate my definite integral mathematically. Okay, so that's what's going on. I wanted to highlight the area under the curve again. This is another type of problem that you'll see in your homework maybe. And it wants us to find the area of this blue shaded region. Okay, great. You know what? I know geometry, right? I can figure this out. Let's see. 1 to 2, this is 1, this is 3, so I have 3, the area of this bit here is 3, and then it looks like, what's going on here? Maybe this is a quarter. It's not a half, that would be a half, right? Maybe that looks like a quarter. So I'm going to say that the area here is 3.25. I just did it geometrically on the graph here. It's a really easy area to find geometrically. But let's do this with some calculus. How would I do this with some calculus? Well, I want to get it in this form, and notice that they put an f of x here. Technically it's an f prime of x, but we're just thinking about the function on the graph. This will be the function on the graph. Okay, so we need to identify a, b, the function, and then we can figure out the area as well. I think a and b should be pretty clear on here. We're going to have to pick the endpoints, the limits on this function. You can see that the blue area starts at x equals 1 and ends at x equals 2. All right, so we're going to integrate from 1 to 2. What are we going to integrate? Well, we need to integrate this line. We need the equation of this line. You know how to find the equation of a line, right? Y equals mx plus b. Well, I can read the b off the graph. There's a +4 in here. And then I know there's a negative slope. What is it? -4 if I go down 1 over 2, so -1/2 x. So that is going to be the function that I am integrating. Okay. So when I do this, I'm going to take the integral from 1 to 2. -1/2 x plus 4 dx. Let's integrate it. This becomes 1 plus 1, 2, so I get a negative 1/4. Oh, I told you all not to do that. Negative 1/2 times 1/2 x squared plus 4x. All right, so negative 1/4, and I'm going to evaluate that from 1 to 2. Negative 1/4 x squared plus 4x. So, did I run out of room here? Let's put this up here. I'm just going to do this right here. So I'm going to get negative 1/4. I'm going to put in my endpoints. 2 squared plus 4 times 2 minus, that's the first term, negative 1/4, 1 squared plus 4 times 1. Okay, this looks like a lot of work for something that I already figured out, 3.25. Let's see if we get to 3.25. We have negative 1/4 times 4, so we get negative 1 plus 8 minus negative 1/4 plus 4. So we get 7 minus 3.75, which is 3.25. So that's what goes here, 3.25. Notice that I did geometrically, super easy. When you're given the area here that are very easy geometric shapes. But that's how you would do it with the integral. And it should match up, right? You should be able to show your work of the integral mathematically and have it match up what you saw on the graph. On the previous problem we did, it wasn't that easy, right? You can't geometrically find this area. It goes up to what, 2469. There's no nice, right, boxes going on here. That's the nice thing about the integral, is when we're given some arbitrary shape, we can easily find the integral. 1645 we got, right? Whereas here, I don't know if I would have went through all this work in order of the calculus, the actual math of it, in order to find this number. But you should be able to show that work and make it work out. Okay. Let's look at a physics example. And what I want to do is a little bit of interlude in here about the difference between definite and indefinite integrals, because we've done both of them so far. As a physicist, right, when I'm thinking about what I use integrals for, definite integrals are usually used to calculate quantities. You just saw that. I use a definite integral to calculate the 3.25. Or I may do some proofs where we have definite endpoints for our events or processes. So you may have a block sliding down a curve or something. You may have an ideal gas that is being compressed under constant temperature, right? There's different endpoints for events or processes that we will be interested in, and we can use a definite integral to look at that. Indefinite integrals we can use most often to derive general formulae or to verify or prove formulae, because as physicists we like to prove things too. Understanding where equations came from rather than just that there is an equation. So I picked an example from intro physics, physics 1 stuff. We're given a position function. Oh, no, we're given a velocity function, sorry. They put an F here, but I like putting a V here just to remind myself, right? Letters mean things to physicists. Destiny rides her motorcycle with a velocity, and this is the velocity function. 1/2 t squared minus 1/2 t minus 2. It's a parabola where, I'm just changing this to V as well, where the velocity is measured in feet per second and t is measured in seconds. Okay, so here's the velocity function, right? Okay, and we know that velocity is the derivative of the position function over time, right? This is the position function. We take the derivative of the position function over time, and we get the velocity. We know that's true. It says find Destiny's displacement and her total distance traveled. Okay, so words mean things. You all know that. Displacement and distance traveled are two different things. Displacement means Where did it start? Where did it end? What's that absolute difference there? Distance traveled wants to know where did it go total? What's the total path traveled? So we have two different quantities we need to calculate here. So what I'm going to do with this definition of velocity is I'm going to do a little bit of algebra on here. You're not going to be surprised maybe for me to do this. I'm going to bring the dt over onto this side, and I'm going to have the derivative of x sub t equals velocity dt. And notice that the velocity is a function of time as well. All right, dt. If I take an antiderivative or an integral on both sides, what I'm going to get from this equation is it's going to tell me that if I want to find the position function, I'm going to take the integral of the velocity function with respect to the time dt. Okay, well that's convenient because I know the velocity function. And what I'm going to do is an indefinite integral. Remember on the previous slide I said there's different uses for the definite and indefinite integral. I'm just going to do an indefinite integral here. Notice that I have do I have the original velocity? Does it tell me? Yeah, it looks like the original velocity is -2. Do I know the original position? I don't know the original position. It just wants displacement and distance traveled, so I don't really care where it started. It's just like, where did it end up from there? So let's do an indefinite integral here. The position function with respect to time is going to be given by the integral 0.5t squared minus 1.5t minus 2 dt. I can do that out real quick. I'm going to add a +1 here. So I'm going to get 0.5 divided by 3t cubed. Everybody okay with that? Do it a little bit in my head. I have a 1 here, so I get +1 minus 1.5 over 2t squared minus 2x. And technically there is a +c here because I don't know where it starts in terms of the position at time 0. It doesn't tell me anywhere in the problem where it starts at position time 0. So I'm just going to leave the +c there. Okay. And that will be my position function. I'm just going to leave it like this. So let's see, if I want to find displacement, they give me endpoints here from 0 to 6 seconds. So when I look on here, okay, here's 0 seconds, right? T equals 0. And here's 6 seconds. X equals 6. And when I think about the integral being the area under the curve, I'm going to have this area here, which is under the x-axis. This will be a negative value. And then this area here, let me do it in a different direction maybe. Will that help you? This is going to be a positive area up here. So when I find the displacement, I'm taking this negative area and adding the positive area, and I'm going to get a value. Well, how do I do that? Well, I'm going to do that with a definite integral. What I'm going to do is say that the displacement, right, displacement delta x equals x of 6 minus x of 3, right? If you know physics, if you know introductory physics, the basics of motion and definitions of motion, you're not going to argue with me on that. And I know the position function. There it is. There's some arbitrary constant here, but when I subtract, I'm going to have the arbitrary constant in this term and the arbitrary constant in that term, and it's going to subtract itself out. So all I need to do over here to find the displacement is I'm going to plug in 6 and then, oh, sorry, this should be a 0. I don't know why I put 3 in there. X of 6 minus x of 0. When I plug in x of 0, t of 0, t equals 0, time, getting my time and my x's confused here. I'm going to plug in time equals 6 and then time equals 0. I think the time equals 0 when you look at this is going to be trivial. There's a 0 there, 0 there, 0 there. So this term becomes 0, the second term. So I can go 0.5 divided by 3 times 6 cubed minus 1.5 over 2 times 6 squared minus 2 times 6. All right, that's the first term. That's x of time equals 6 seconds. And then this term I already did in my head, 0. Okay, so when you calculate this out, you can go ahead and take a moment to do that on your own. You may not be surprised to find when I take this negative area and add on this positive area, there's more negative area than there is positive area, and I get a -3, which tells me that it moved backwards or in the negative direction 3 feet, right? We have units here, 3 feet. Velocities in feet per second, so I know that the position, the displacement had to be in feet as well. So -3 feet. So that's how to do that. I turned the indefinite integral into a definite integral. I evaluated it from 0 to 6. Okay. To find the distance traveled, I think this is going to be a little bit harder because if I want the distance traveled, what I want is this negative area, the absolute value of this negative area, and then add on the absolute value of the positive area, right? Distance traveled says I don't care which direction, I want the total value. So I'm going to take whatever this negative area is, take the positive of it, and then add on this positive area, okay? So the distance, what I'm going to look at is to find this here, this area here, I would take the position at 4. Notice that this point in here, where it crosses the t-axis, this is t equals 4. Do you all see that? Okay. So I'm going to have to divide it up into 2 different portions here. The absolute value, this is our negative portion, right? From 0 to 4, this is our negative portion. I'm going to take the absolute value of it. And then I'm going to add on, of course, the absolute value of x of 6 minus x of 4. That'll be that positive area. I don't really need absolute value signs around it, but I'm going to remind you that's what I can go ahead and evaluate it, right? 0.5 over 3 4 cubed minus 1.5 over 2 4 squared minus 2 times 4 minus 0, x of 0 we already said was 0. I'm going to add on x of 6, which we already know, right? X of 6 we already did over here, -3. I'm just going to put that in here, -3. You could evaluate it again if you want to, if you have that time to waste or whatever, but I'm not going to. Minus x of 4, whatever that value is. Again, it's this thing, whatever that thing is. So I'm just going to put x of 4 there. Whatever I get, I'm going to just put the same thing there in the next line. So when I do this, x of 4, when you evaluate this term, it becomes a -28 thirds. And you can go ahead and do that on your own. I'm fine if you do that. I think I ran mine through a calculator, did it on another sheet of paper. But so I want to take the absolute value of that. I subtracted 0, but that's trivial. Plus -3, the absolute value of -3 minus -28 thirds. Okay. So when I do that, I'm going to get positive 28 thirds. I'm going to take the absolute value plus 28 thirds minus 3, right? I have a minus and negative, so I get a positive 28 thirds minus 3. That becomes positive 19 thirds, and when you add 28 to 19, you get 37 over 3. Okay, so the distance traveled is going to be 12 point, what, 1/3 feet total. Okay, so it moved backwards 3 feet, but total it traveled about 12 1/3 feet. The next thing I have for us is integration by substitution. I dealt with very simple power functions. You may say, well, an x to the fifth is not simple, but it's very simple compared to other functions that you could be working with. All right, and this deals with composition of functions. Notice that if I put a function into another function, that is going to be the most the reason to use integration by substitution is to notice that if you're given a derivative and it seems to be the derivative of a function within a function, all right, we can do integration by substitution. And what I'm not gonna talk about this out right now. I'm gonna leave the example to show how to use this heuristic formula. Okay, but chain rule is sort of the basics of this, and remember, it's a skill to recognize a useful arrangement of composition of functions. Okay, so let's see, chain rule. What if let me remind you of the chain rule. 2x squared plus 4 squared. If I wanted to take the derivative of this with respect to x, all right, what I'm going to note, and you may have used a substitution on this one, I have to take the derivative of the inside and the derivative of the outside. Okay, so if I take the derivative of the outside, I'm going to get 2x squared plus 4 to the first power, and then I would multiply by the derivative of the inside, which would just be 4x. Okay, so that would be the derivative, but we're saying if you're given this and you need to integrate with respect to dx, how do you get from here to there? Well, again, we're going to use a u substitution. If you did a u substitution before, you would let this thing in the parentheses equal u. We're going to do the same sort of thing for here. We're going to do a substitution for integration and go backwards. Okay, so let me show you an example. Here, you're looking at the example. We have a definite integral from 9 to 4, or 4 to 9, sorry, 4 to 9, of some complicated function raised to a power. And then what I'm going to note, and this is sort of maybe what you're doing in your head, is we have something raised to a power. If there's something raised to a power, a good option is that whatever's in these parentheses is going to be your u value, your substitution. And when if I let u equal this, z squared minus 13z plus 36, if I find du, if I take the derivative of this function with respect to z, right, or if I could do this, du dz equals 2z minus 13. Right, I just took the derivative of that with respect to z. Notice that's the term I have over here. Right. What I'm going to say is du. I'm going to do a little bit of algebra. I'm going to move the dz over to the other side, so I get 2z minus 13 dz. Or I could say dz. Notice that. If I do some algebra, if I isolate for dz on its own, I'm going to get du over 2z minus 13. So wherever I see dz up in the original integral, I can plug in that thing. Well, you can see that it does nice stuff, right? We're going to have the integral of u to the 10th times 2z minus 13 du over 2z minus 13. That's what I was saying. That's not very interesting, right? So that's what I'm going to get is 10 u to the 10th power du. But I still need to figure out the endpoints. And why I picked this example is because that's what students forget to do. And when I first learned integration and substitution, I forgot to do this. They would keep the same endpoints, and that is not correct. That is not correct. We're doing a substitution for u, so we need to figure out if z equals 4, what does u equal? If z equals 9, what does u equal? And those, I'll do u1 and u2, right? Those will be your new endpoints. You need to figure out your new endpoints if you're doing a substitution. Okay, so if I plug in 4 in here to figure out my new endpoint, I'll get 16 minus 13 times 4 plus 36, which 13 times 4 is 60 or 52, which this turns out to be 0. So my lower endpoint was 4, now it's 0. Before this is a z value, now it's a u value. When z equals 4, u equals 0. So I have to change my endpoints. Let's do the same thing over here. I'm going to get 9 squared, which is 81, minus 13 times 9, which is 7 to 117. Is that what that is? 117. Plus 36, 81 and 36 is 117, minus 117 is 0. So our new endpoint at the top is also 0. That is not a mistake. So you may see right now that the answer to this is 0. If I integrate from 3 to 3, the area under the curve is going to be 0. If I integrate from 492 to 492, the answer is going to be 0. Although that's trivial, that's not hard to figure out, and I integrate from the same endpoint. Let's integrate this, right? I'm integrating from 0 to 0, u to the 10th du. This becomes, I'm going to add 1 here, so I get 1/11th, u to the 11th, evaluated from 0 to 0, and again, the answer is 0. Okay. But the big highlight that I want you to take from this slide, from this example, is you need to reevaluate your endpoints. You can't keep the same endpoints. You need new endpoints, all right, when you do a substitution. The next thing I have to talk about is special functions. Now that you kind of know how to do definite and indefinite integrals, you can use an integral table to find different integrals. Of course, there's integrals for trig functions. Okay, we know the derivative of cosine is sine, so if I want to find the antiderivative of sine, I know it's cosine with a negative sign. There's a negative sign in there. Okay. Cosine is sine, tangent has a natural log of an absolute value of a secant, which is kind of interesting. Secant squared is tan, and cosecant squared is negative cotan. Okay, so we can keep all those in mind. For physics, for the most part, we will be using, especially at introductory level where we kind of keep things simple and straightforward, we might be doing sines and cosines. You may see a tangent every once in a while, but for the motion that we study, it's well modeled by sines and cosines, so you will see those integrals most often. Okay. Second set of special functions, the integrals of special functions, is one of our favorites is the integral of the exponential e to the x. It is very simple, e to the x. We love that one. We love integrating e to the x because it's the same thing back. It's a very useful function and models well harmonic motion, any harmonic motion. The integral of a constant to the x power, right? You can see that there's a natural log in here. I don't see this. We might see it like if something doubles at some function of time, right? The population with respect to the time is, it doubles, I don't know, in some function of time, right? 3t minus 4 or something like that. So you'd be able to find that, that integral. If I have the integral of 1 over x, the integral of 1 over x, which I'm going to note that most often we use this a lot in physics. This is one that we use a lot in physics, and you'll see it more often in 1 over r dr when we're integrating radially rather than a Cartesian x. That's going to be a natural log. We also see this when we integrate using the ideal gas law, and we integrate for an adiabatic process, which if you are in physics 2, you'll get to adiabatic processes. The pressure is a function of volume, and we integrate with respect to volume, and it's a 1 over thing because of the ideal gas law. We're going to end up with a natural log term there as well. So you'll see natural logs. I would say those are the 4 that you'll see most often, is sine, cosine, e to the x, and 1 over in an inverse function. Okay. There is the natural log x. If you take the derivative of natural log x, you can see there's a couple of relationships there. And there are integral tables. I don't necessarily expect you to remember them in physics. A calculus teacher may expect you to remember them. I don't necessarily, but it is something that we'll do repeated ones, and you will probably end up committing them to memory on some level. Let's do an example real quick for the cosine. Okay, we're going to do a special function with substitution. Notice that this cosine isn't just cosine x, it's cosine of a bunch of stuff. So I'm going to let u equal y squared minus 12y plus 32. So then du, and this is another way to do it, du is, if I just do it this way, 2y minus 12 dy. Remember on the previous slide I put the dy down here and then moved it over. I'm just going to put it on the end over there. So I can see that dy equals du over 2y minus 12. And I can make that substitution back up in here. So this is u. This will be du over 2y minus 12. And notice that conveniently cancels. Again, we're picking nice functions. Cancels with that. Okay. We need to evaluate our endpoints now. We have 0 and 3. So when I plug 0 in, so when y equals 0, u equals 32. And when y equals 3, u will equal, what, 9 minus 36 plus 32, which is... Sorry, I was doing some things in my head here. 5, isn't it? It's a nice round number of 5. So very interesting is that at my lower endpoint I have a larger value, and at my larger endpoint I have a smaller value when I do my substitution. Okay, so how do we deal with that? The easiest way to deal with that is to reverse them and put a negative sign out front. Because I will tell you the integral from, let's say, 32 to 5 is going to be negative the integral from 5 to 32. Okay, so that's the principle that I'm invoking there. Okay. So let's put all this together. Let's put it all together. So I know that the original function f of y will equal negative the integral from 5 to 32, right, of cos u du. I don't see anything. My 2y minus 12 canceled there and there. I'm left with cos u du. And I'm evaluating from 5 to 32. Not 32 to 5, 5 to 32. We always go from lowest to highest, all right? When I look back at my special functions, let's look back at my special functions here. I have the integral of cosine u. The integral of cosine is sine. Okay, so I can go in here. I'll have the negative of sine u evaluated from 5 to 32. All right. That's great. We can get our calculators out. You want to get your calculator out and evaluate. When we evaluate this, again, we're going to do the negative of sine 32 minus the negative of sine 5. All right. Or you can do sine 5 minus sine 32. Okay. We're going to get sine, I'm going to do it this way. Sine 32 is 0.55. I can't read my number. Maybe that's a 143. Minus the sine 5, negative 0.95892. Okay, you can run those through your calculator to double check me. I'm pretty sure. And when you add those, subtract those, add those two together. Oh, sorry. This plus becomes, this and this becomes a plus sign. This should be a plus sign here. Okay, so I'm taking a negative number, adding on another negative number. I'm going to end up with a negative number, negative 1.51035. All right. So that's the special function wasn't very difficult here. We just had an integral of cos, which is sine. But the harder part here was the remembering again, and this, I like repetition, remembering to do a u substitution. When you do a u substitution, you have to reevaluate your endpoints for your definite integral. Okay.